This is our lecture on lateral and earth pressure distributions. For announcements, we have our basic skills test, the last one. It'll be on this Wednesday, November 29th, and our homework was delayed to be due on Monday. This covers the textbook chapters 13.1 through 13.9 and course objectives 56 through 60. So we're still talking about our shear strength of soil and applications of that for design. So here are the course objectives. We're going to talk about Rankin's earth pressure theory, which is what we use to determine the pressure pushing on the wall so we can accurately design the wall. We'll talk about active, passive, and lateral earth pressures. We will also talk about how it's derived and how we use the Mohr circle to look at the failure envelope. We'll also talk about the Mohr circle and the origin of the planes concept to analyze stresses. And then we'll talk about different retaining walls, conditions for the surface. So these are the types of questions that will be on the exam as well as on the FE exam. So for lateral earth pressures, most of the applications are related to retaining walls or basement walls. We also have buried pipes, anytime you do anchoring, lateral loads on piles, as well as tunnels. So all of these are pressures that are pushing from the side onto the structure that we're going to design. So the soil is going to push, and we need to design how this wall is going to resist that pressure. So there are a lot of different types of retaining walls and retaining structures. All of them are developed slightly differently. So most of the ones you probably have seen or think about when you think of retaining walls are gravity walls. We'll talk about those. Cantilever walls, counterfort walls, and buttress walls, and crib walls. So these are pretty much to hold things back. Then there's also semi-gravity walls, sheet pile walls, typically for excavations, anchored sheet pile walls for deep foundations and excavations for buildings, braced sheet pile walls, and reinforced earth walls. So here are some of the images to look at the different types of walls. The most common and easiest one that's been built for a long time are just traditional gravity walls. So you can see all these different types of gravity walls. You can use bricks, stone, they have plain concrete, you can have keys in it to help prevent from sliding. Then we have our cantilever retaining wall, so that this side of the wall has a place for soil and it helps with resisting the push of the soil onto the wall. We also have counterfort or buttress wall. So this part behind the wall is designed called a counterfort. It allows you to have some kind of structure that helps reinforce the wall so that the pressure pushing on it resists that. We can also have crib walls. Here's an example of one down here on D. You can have the stretcher and headers. You can fill this with soil to push back the whatever you're trying to retain. A semi-gravity wall is basically the concrete. The weight of the wall itself is trying to help push back or resist that sliding action. And then finally, we have abutment, bridge abutments. So here's the wall that would be built for a bridge abutment, and this would be soil or a reinforced, geo-reinforced soil with a membrane to try to prevent this from sliding and pushing out our wall. So the three types of concepts we're going to talk about today are for lateral earth pressure. So the first one is called the at-rest condition. That means that there's no soil movement. So at rest, there's nothing's moving. So that's going to be this first condition here. We'll talk about that one. Then we also have the wall moving away. So here, that's the second one. And then the third one is the wall is moving into the soil. So here's the wall moving away. That's called the active condition, actively moving. And then the third is the wall is moving into the soil. You can see it's being pushed here or into the soil, and that's called the passive. So once again, the three types are at rest, no movement, away, active, where the wall is pushing, the soil is pushing the wall away. And then finally, this wall is being pushed into the soil. That can be from an anchor or like a strut or something that's pushing the wall into the soil. So for the first case we're going to talk about is at rest. So at rest is when the pressure exists in the ground at all times already, and it's long-term condition. It is called K naught. So often you'll hear people call this the K naught condition or the at rest condition. And that K naught is defined as the horizontal force or stress over the vertical stress. So it's whatever's happening in the horizontal direction with respect to what's happening in the vertical direction. So oftentimes we know how to calculate vertical effective stress. So we can calculate horizontal effective stress by knowing this K naught, this at rest lateral earth pressure coefficient, and then multiplying it by gamma and the depth. So this is also, it's in terms of effective stress. So there's a lot of different empirical relationships to determine what K naught can be for soils. For coarse grain materials, sand, typically the relationship is 1 minus sine phi. Remember, this is the friction angle from our triaxial testing. For clays, you can also have, if you know it's over consolidation ratio, then you're able to use this correlation, and these are the most two commonly used correlations to determine K naught. When we're talking about designing at rest, we typically think of dry soil. So if you're in dry soils, you can calculate the horizontal stress by knowing the K naught from a correlation or if it's given to you. And then you basically assume that the distribution of soil, the pressure pushing on that wall, is this triangular shape right here. And if you know this, you also know that the resultant of that stress distribution, the force of that resultant, acts about 1/3 up from the bottom on a triangle. And here's the equation you would use to calculate the resultant force. It's 1/2, because this is an area of a triangle. The width of this, the base of the triangle is K naught gamma H, which is the horizontal stress. And that is then the height of the triangle. So it's the area of the triangle to find out what the resultant force is. If the soil has partially submerged water in it, then it's going to change the shape of the distribution of pushing on the wall. So when there's water, so in this case the water is here, this top half is dry, so it acts just like we said, a triangular distribution. But now we have this water pressure and we still have another, here's the water pressure, saturated unit weight of water. This is the pressure of the water, and now the change in shape looks like this for the part that's saturated. So typically, the effective horizontal stress is K naught times the effective vertical stress. So that just means that the horizontal stress, effective, is K naught, because we just said what K naught's the ratio between the two of the vertical stress. Water adds additional force to the wall, so you can think about that. It's more force pushing on the wall. It is typically calculated using the area of 3 triangles and 1 rectangle, and the sum of the moments about B to find the height of the resultant force. So B here is the base. So you find the sum of the moments to find the height of the resultant force. The second case is the active. So now the soil is pushing the wall out. So in that case, what's happening is if you think about your Mohr circle, you have your stresses. So remember in Mohr space, this angle here is 2 theta, and this sigma 1 is the maximum stress, and sigma 3 is the minor stress. And this was our equation from Mohr circle that relates the stresses. And we also said that this theta is 45 plus phi over 2. So what is happening is when we first have our wall built, this is the vertical stress, and this is the horizontal stress. Now, what's going to happen is the vertical stress is staying constant. We're not adding any additional load to the vertical, but the wall is moving outward. So that is reducing this horizontal stress. So we're having this smaller stress, the minor stress, is actually going to move this direction. So if we watch, what happens is as we move and decrease that horizontal stress because the wall is moving away, we're going to keep going until it fails. And what happened is that we got this horizontal stress so small that the Mohr circle intercepted the failure plane. And if we reduce it enough, this angle of failure theta, is 45 plus V over 2. And this is the equation you can use to determine what the stress would be in the active case at failure. And that's how we do it. And notice that the active coefficient, this Ka, is tangent squared 45 minus V over 2. That's important to notice. And that the active case, this coefficient for the active case, is just calculated taking the tangent of 45 minus V over 2. And the failure plane from the horizontal is 45 plus V over 2. So this is called the active Ka condition. So here's another example of the active condition as it's decreasing the horizontal stress, and now it's failed. So those were the equations that we talked about in the past, and you can use them to determine the vertical or the active case. And here is how they're derived. And you really don't need to go through the derivation, but you make sure you know how to find these, especially on the FE exam or on the final, you'll be given these equations. So for the active case, here's how they're derived. They basically substitute in the information, and the main two things you need to remember is that the active K, coefficient of Rankin's active pressure, is this equation, and here is the failure plane. So if you have a cohesionless soil, then you're able to basically just use this regular equation here. We just went through it. In the active case, it's still a triangular distribution, but instead of K naught, now you use this Ka term here. You can also calculate the Rankine active if there's cohesion. So cohesion changes it because now you have this term here, which in the prior example was 0. If you have cohesion, you're just going to plug in for this information. It's still, now you're going to have to take into, this is the triangular distribution, and this is the distribution that is added from the cohesion. It's subtracted from the cohesion. So this is the equation, or in the shape, and the equation that you would use when there's cohesive. So each type of lateral earth pressure will have 2 or 3 different types of equations. They'll have one for non-cohesive, and one for cohesive, and one in case there's water. So on the exam or in the FE handbook, you're going to want to look at your case and then determine if it's got cohesion or if it doesn't, and then which case you're looking at rest or active, and in a minute we'll talk about passive. So here's just basically the how you take into consideration if it's horizontal ground is level. So here, this level. So you just use the equations we've been discussing. Or if there is an incline backfill, you have to take into consideration this additional soil behind the wall. And so now you're going to use a different equation for Ka. You can also use charts. So here's an example of a chart from the book. This chart basically has the different angles of soil and the friction angle of the soil. And you basically find, say that if it's level ground, that's 0. Then these, if you have different friction angles, this would be your value for Ka. So it's just plugged into this equation. If it's 5 degrees, these would be the values based on different friction angles. So like, for example, 28. The last case we're going to talk about is the passive pressure, where the wall is being pushed into the soil or moving into the soil. Here's, once again, the Mohr circle. So these are the same equations we've seen prior. In this case, what's happening is the horizontal pressure is changing, the vertical is still constant. And so now we're going to see what happens as we increase. We're going to increase the vertical pressure. So basically the wall is moving this direction, pushing into the soil, and the horizontal stress is increasing. So it's going to increase until it fails. And now the angle here is, once again, 45 minus V over 2. The passive pressure is the opposite of the active. Notice here's the plus, whereas before, when we had the active case, if you go back and look at that, we had the negative. Now we have, sorry, that's a negative. Let's go back here. Here we go. So in this case, for passive, it's a positive. When we had the Ka, the equation had the negative in it. And the failure plane now, instead of being 45 plus phi over 2, is 45 minus phi over 2. So it's just the opposite. So prior to this, we were talking about active, the wall's moving out. And so we had the different sign convention or different signs. And now the wall's being pushed in and we have the opposite sign. So here's an example of what's happening. We're increasing that pressure. And as we increase that pressure, we have failure. So this one shows the difference between the initial condition and the passive condition. So once again, the equations can be derived from the Mohr circle. The main thing you need to know are these two equations, or you'll be given these two equations. You can calculate them once again from a triangular distribution if there's no cohesion. It's just like we did with K naught and Ka, but now you use a different coefficient, use the Kp coefficient. Here's what happens if there's cohesion. So now we have this C. We can't put a 0 there. We actually have to calculate it. And also the same way, you can look at if it's inclined. You can calculate what happens if there's additional soil behind the wall. And you can use that, and there's also charts. So the last thing we need to talk about is a different, instead of Rankin's active pressure and passive pressure, one that's based on Coulomb theory. The reason we talk about Rankine versus Coulomb is for Rankine, the assumptions are that the soil is homogeneous and isotropic, the wall's moving sufficiently to create active or passive condition. We're assuming a very long wall into the page. It's a 2D problem. The big thing is that we assume that there's no friction between the wall and the soil, and this is not a very accurate assumption. And then finally, the resultant force is inclined with the angle to the back slope. So as a result of these assumptions, an element of soil behind the wall only has principal stresses acting on it and no shear stresses. And we know that's not exactly accurate. So Coulomb came up with a theory to account for the friction and to account for the wall slope. It has the same assumptions as Rankine, plus now it has friction between the wall, and it changed the resultant to be inclined with from the normal to the back of the wall by the angle of friction, this delta. So here's the equation. Basically, all the assumptions are the same, but now you're going to have different equations for calculating Ka and Kp. So here's the equation you would use. Here's the assumptions of how it was set up. But basically, the idea is you would use this Ka in calculating the equation in the equations that you're going to use. So here is the table. Once again, you can take into consideration if there is a slope or inclined plane behind the wall, and you can calculate your Kas and ultimately your horizontal stresses. Here is the equation for passive, and these are how they derived it, but basically the idea is that now it's going to take into consideration friction behind the wall. Here is the table for if you're going to take into consideration any angles happening behind the wall, and here is how you calculate the stresses and the resulting force. So why do we care about all this? When you're designing a wall, you're mostly concerned about how much pressure is pushing on the wall and how much the wall is moving. So if you look at the lateral earth pressure versus how much the wall is moving, you can look at this chart here. This is the horizontal stress. This is how much the wall has moved. And typically in loose sands, the wall movement is about 0.001 for very loose sands, so a pretty small ratio. Here's the at-rest condition. Here's the active condition. And we'll go through an example of how to use this chart in one of our examples in class. So here's an example. If it's a 20-foot high wall of loose sand, Typically in the active case, it moves 0.2 of an inch. In the passive case, it moves 2 inches, which is quite a bit. Lastly, we're going to talk about the factors that affect lateral earth pressure. There's a number of things that can affect it. So typically the soil type, the unit weight, the friction angle, the cohesion, if the soil has a tendency to creep, how far the depth of below the surface, how deep the wall is, or how high the wall is, where the location of the water table is. We talked about that. Additional water adds additional pressure. If there are any surface loads, for example, a bridge abutment or a crane or anything like would be at the top of the wall, a house, you have to take that in consideration. If there's allowed to be drainage or no drainage, if water builds up, that's additional pressure. If water's allowed to drain, then it hopefully would stay dry. And if there's any stress history, changing of loads over consolidation ratio. And then any type of seasonal water table fluctuations. If the ground slopes, we've already looked at how we take that into consideration. If water freezes behind the wall, that can add additional stresses. And fluctuations in temperature from hot to cold can change how the soil, if there's cracks or anything pushing on the wall from the soil. And then if there's a lot of wall friction, that can add to the additional stresses on the wall. And if the wall's moving. Finally, if soil is removed or erosion is occurring between the wall and the soil, that can cause changes in the pressure. And lastly, dynamic loading such as earthquakes or vehicle motion. So in the end, will the backfill be drained is one of the major concerns. If it's not going to be drained, you're worried about water pressure. If it is drained, you're going to design for the active case. Your goal is to make sure to avoid water and design weep holes. And you're mostly concerned also about what kind of backfill will be used. The best is sand because it allows free draining. Clays are typically very hard to compact and they have higher pressures. You're concerned also about how much the wall is going to move. And the movement depends on which direction. Is it going to be an active or passive pressure? So you calculate those. If the wall cannot move because it's basically very stiff or it's being pushed back or held in some way that doesn't allow movement, then you're going to use the K0, which is the at-rest values. And will the surface of the backfill support loads? So if that is the case, like for example, cars or train or something that like large crane, you have to add additional horizontal pressure to the surcharge. So in class, we will talk about examples from these three different cases.